this is SAP 2000. Let me just open a new model, and let's this time use the example of a two-dimensional frame, let's say a reinforced concrete frame. So let me just start with a new model, and let's say that I start with grid only. I am selecting Newton millimeter units, and with grid only because I want a two-dimensional frame. I can also use this template, but let's say I start with grid only. Uh, let's say that in X direction I want 4 grid lines, in Y direction 4 grid lines. Sorry, let's have the model only in the XZ plane. So Y direction will not have any grid line. So I just put 0 here. Let's say it is a 5-story frame. So let me just have 5 here. Let's say in X direction it has a span length of 6 meters. Y direction doesn't matter. And the story height is, let's say, 3 meters. And the first grid line should start from 0, 0 origin. And I click OK. If I want an XZ, uh, if I have a model in XZ plane, I think I should have at least one line in Y direction also, so that the program can uh, show me the grid lines. Yes, you can see here that at least I must have one line in Y direction also in order to construct a grid view in the XZ plane. So now this is the 3D view of my model, but I can, in this left hand side, I can open an XZ view also. So this is my grid lines for my frame, let's say. And let me quickly define the steps for fiber modeling. The first step would be to define the materials, the nonlinear stress strain material constitutive models for my materials, for assigning it to the concrete and steel fibers, because it is a reinforced concrete frame, let's say. So the first step is defining the materials. So if I show you these slides here quickly, maybe let's assume that this is our modeling approach, that we will be having some, for example, this is our length, and at two ends of my columns I have the fiber section, concrete and steel fibers, represented by this particular symbol, and the shear behavior will be uncoupled from the flexural behavior, and it will remain elastic, which is represented here by a linear shear spring here. And these fibers will be just lumped at both ends. In between is, let's say, the linear elastic frame element, because I expect the nonlinearity only at the ends of this column. So there will be some part of fiber which are running along some part of the length on one end and some part of the length on the other end, and then in between is the elastic element. You can also imagine this particular figure, because it looks very complex. Imagine it like this, that you have this particular column, and it is like this, maybe, yeah, like this, and it has for some part of the length at one end it has those fibers which are running along the length, maybe like this. And then in this is material fibers made of either concrete and steel material fibers, and then on the other end also it is like that, right? So it has the bundle of fibers, concrete and steel fibers, on the other end also, and in between them is the linear elastic frame element, linear elastic frame element, which we generally use for elastic modeling. And this length, that for how long this material fiber should extend to incorporate the nonlinearity, it is a matter of research. Sometimes you will see that researchers proposed empirical expressions for this plastic length of different elements. Some, for example, say that it can be half of the cross-sectional dimension. If, let's say, this is the cross-sectional dimension d, it can be half of that. Some say it can be full length of the cross-section, and different researchers have their own expressions or ideas about how long this length should be. the program allows you to define that length, and it can also allow you to define it for whole length also if you want, but that would take more analysis time and the model will be heavy, and the nonlinear action may not occur in the mid span, and therefore you may not require material fibers there. So this is how my model, my columns model, nonlinear model would look like. And I will repeat again that these material fibers will only account the flexural nonlinearity. So fiber modeling doesn't account for shear nonlinearity, it only accounts the flexural nonlinearity using material fibers. So fiber modeling actually accounts only for the flexural nonlinearity, right? And shear behavior need to be modeled separately if you want to make it nonlinear. You can also have what we call as a shear hinge, but if you don't have a shear hinge, by default you are using a linear shear behavior, right? So if we don't have anything about shear in this model, by default it is linear and it is uncoupled from flexural action. So we will be just having fibers, which means we are only accounting for the moment nonlinearity or flexural nonlinearity. For this particular demonstration, let's assume this is our nonlinear modeling scheme. Now we are ready to go to SAP 2000 and we can see how we can implement this nonlinear column modeling in our two-dimensional frame which we have just started. So let's have the first step, which is the material definition. We need to tell the program that our concrete and steel fibers will have this particular stress strain curve. So let's say that I have a default concrete material. Let's make a new one quickly. Material type is concrete, and then we can just click OK. We can add it, modify, and then give it name, for example nonlinear material. Actually nonlinear concrete should be more obvious, concrete. And then the important point, all of these properties will be used for linear analysis, which we have done already in last session. But more importantly is there is a option called switch to advanced property display. When you click on that, you will be given an option about show material properties, and here in that you can define some basic inputs which are required for linear analysis. But more importantly, here you have an additional option called uniaxial nonlinear data. You can click on that, and this new form will allow you to define the stress strain curve of this particular material. So let me just use, you can either use a parametric, which means a predefined model for defining the stress strain curve, or you can also use what we call as a user defined option, in which you can enter the values of stresses and strains for different important points and program plots that curve for you. If I want, I can simply use Mander's concrete model or a simple parabolic concrete model and then convert it into user defined. So program will be using these basic inputs like elastic modulus and all that, and these parametric strain data inputs to plot the stress strain curve based on either of these two models, and then you can convert it into user defined and also modify it if you want. So let's say that because I will have a limited time, so I may not be able to go into detail of all the options, but let's assume that I am using a simple parabolic model and I have this elastic modulus on the previous form, and I have these input parameters like what is the strain corresponding to Fc prime, what is the unconfined strain capacity, which is the ultimate point, and what is the final compression slope, how the curve should go down, and I can simply convert it into user defined by selecting simple. So you can see here that the program used that simple parabolic model which is embedded in the options, and it plots the stress strain curve based on your given inputs. The positive axis is the tension axis, therefore we have very small strength, and then negative axis is the compression axis, so we have the parabolic stress strain curve like this. I can click on this show plot to get a more enlarged view you can see here this option, and you can just play with it when you have time. Uh, this was the first part of defining nonlinear material, which is the backbone, which means the actual stress strain curve, monotonic curve. The second part is this one, which is the acceptance criteria. See, these are the strain values which you can define on your stress strain curve. First of all, it doesn't have any effect on your analysis, but you can use these values, predefined strain values, to sort your elements or to check whether a particular element have passed your particular acceptance criteria or not. For example, since ETABS use the ASC 41 terminology, so it by default gives you three performance levels, which is called the immediate occupancy, life safety, and collapse prevention, shown by the green, blue, and red colors respectively. And you are allowed to give the strain values for these three levels in compression and tension. Let's say that you give 0.01 as a tensile acceptance criteria for IO level, and after running the analysis you ask the program to plot all the elements with different colors for IO level. And if a particular element is shown in is shown that it crossed the IO level, which simply means that the strain in the material fibers of that element crossed this particular strain in tension or in compression, right? So these are, you can call them as markers on your stress strain curve. Let me just draw it also for you for more clarity maybe here. So you actually give three inputs while defining your material fibers, actually materials for your fibers. One is the backbone, which is this thing in compression or tension depending upon what uh, direction of axis you are using. So sigma and strain. So this is the first input. The second is the acceptance criteria, which is actually three markers on the same stress strain curve corresponding to IO, LS, and CP. IO, LS, and CP. So you give it in compression and tension also, let's say. So after the analysis, what you can do, you can ask the program that, okay, show me all those elements which have crossed CP level. What it will simply do, it will check the strains in each fiber of all the elements, and if it cross this particular number which you have given here, this CP level, it will show you that it have crossed the CP level. So you can check the performance. So performance check can be applied automatically if you define these IOLS and CP values in terms of material strains. This will be for concrete as well as for steel. So second step is defining what we call as the acceptance criteria or capacities of your nonlinear component. Since your nonlinear component in this case is a material, so those capacities will be in the form of strains. But obviously for other nonlinear components you may use a different nonlinear modeling approach, and therefore the deformation measure will be different for your other elements. But for fiber modeling it will be material strains. So IO, LS, CP strains you have to provide in compression and tension, so that you can check the performance after the analysis automatically by the program, but they will not have any effect on your analysis. And third thing is the hysteretic behavior, which means that you are telling the program that how your material should unload and reload uh, during the reversal of forces and different cycles of loading. So that thing is the third input you have to provide. These things you have to provide for each material, whether it is concrete or steel, and this will constitute your first step of defining the fiber modeling. So if I just classify it into different steps, fiber modeling, it will be actually 3 or 4 steps, I think, maybe 3 steps only. One is define materials, define actually the stress strain curve of each material. Second is define the cross section, define cross section. Obviously if you want the program to divide your cross section into different concrete and steel fibers, you have to input the reinforcement in the program. Obviously, the nonlinear modeling will use the actual reinforcement in your cross section as an input, unlike the linear modeling where you don't need the reinforcement for the analysis. So reinforcement, input the reinforcement and cross section size, and each reinforcement will be assigned with a steel fiber stress strain curve, and concrete will be assigned with concrete stress strain curve. So second step is define the cross section including the actual amount of reinforcement and everything. The third step is actually assigning the what we call as fiber hinges, actually telling the program that this length of that particular column should be assigned with fibers of concrete and steel, and the other part can remain elastic and all that. So assigning fiber sections or fiber hinges, right? This will complete our fiber modeling, and then our columns will become nonlinear. When we run a nonlinear analysis after that, the columns, if the applied loading is beyond the capacity of columns, if it is causing cracking, yielding, and all that in our concrete and steel, the program will be able to tell after the analysis, unlike a linear model which will not be telling you about anything about damage. So let me again go back to SAP 2000 after that. So we are at the first step where we are defining the materials for our nonlinear concrete and steel fibers. So here I have already defined a parametric stress strain curve and converted into user defined. If I want, I can change these strains and stress numbers and all that, and it will modify the plot accordingly. This plot, this is tension side, and then this is the bottom side is the compression side. And then the second part is the acceptance criteria. Let me put some numbers in compression. Let's say it is 0.003, then it can be 0.006 in ls. No, it should be maybe 0. Maybe 0.002 can be the IO, or 1 can be IO, 2 can be ls, and then 0.003 can be CP in compression. Three numbers on my stress strain curve corresponding to my three performance levels. In tension, it can be just 1, 0.0001, because it has very small strain in tension concrete. So I can 0.00015, and maybe the third can be 0.00002 maybe. But obviously in tension side of concrete, we can have only one particular performance level corresponding to the tensile cracking only, because we don't have a much non-linear action in tension side. So maybe can have 1.7 maybe. And then show plot. And in ETABS there is an option to plot the acceptance criteria on the same curve also. Let me see if we have a similar option here. Show shear curve, borders and all that. So these are all display options. So it doesn't have that feature, I think. But ETABS show you those 3 points on that curve also, just like I draw in my PowerPoint. But you can give these numbers, strain values in tension and compression, and they will be used for IO, LS and CP capacities. You can ignore tension acceptance criteria by checking this, and you can uncheck this one. And again, it depends on your choice of how you are modeling the tension capacity of column. Another important property which you have to provide for each material is the hysteresis type, and there are several templates available or models available for hysteresis. Obviously, the elastic would mean that the material will simply follow the elastic path while unloading and reloading, but there are different other models available. I would recommend you to please go to the analysis reference manual of SAP 2000, and it will tell you the details and shape of each of these models. So you will be seeing, for example, for how the degrading hysteresis model will look like, how the Takeda model will look like, or how concrete model would look like. Each of the hysteresis model is as we need to define some additional properties also. For example, for concrete, we can click on modify, and then we have to provide what we call as an energy degradation factor. For degrading model, again we have to define a series of additional components. So I will skip that part for simplicity now. Maybe I'll just select concrete here with zero energy degradation factor just for the purpose of demonstration. But the main idea is here you are telling the program how your this particular material should unload or reload. So just look at how these different models look like in different cyclic forces. For example, the analysis reference manual will tell you that, for example, the concrete model may look like this, or Takeda model may look like maybe like this, something like this. So please check the shapes of each one, and you have to decide based on that which unloading and reloading rule is most suitable to model my particular material. So I will be clicking OK and then clicking OK. And now this particular material is a nonlinear concrete material, and it has the associated stress and strain curve with that. So it is nonlinear concrete having a particular strength and all those elastic properties. But in addition also it has the nonlinear stress strain curve, which you can see from this particular button. So obviously whatever FC prime you give here, the program will be using that FC prime in defining the parametric stress strain curve. But obviously you can modify that also later. So here you can see that 27.5 megapascal was my FC prime, and the program used that one, although I converted it into user defined, but the peak value you can see here in compression is the same 27 point, same number. So with this information, I'll just click OK, and nonlinear concrete will be saved now as a material. I can add a new material quickly. This time I can call it rebar type material and click OK. Modify it. Where is that? Yeah, this one. I can modify that rebar material and modify show properties. Obviously its directional symmetry will be uniaxial. It will be a uniaxial bar. Concrete's directional property was isometric. It has all assumed same properties in all directions. And I can give the basic Fy, Fu and all the other basic properties like elastic modulus and everything similar to the elastic material. But now I have an additional option here, nonlinear data. And again I have two options: simple parametric equation for plotting the stress strain curve, or we have the Parkes model. Just like the Mander model for concrete, we have the Park model for steel. I can convert it into user defined, and then I can show its plot, which it automatically calculated using the Parkes equation, and I can modify it if I want. I can give the acceptance criteria and the associated hysteresis type. You can see here in the analysis reference manual that which hysteresis type is most suitable for concrete and most suitable for metallic materials like steel and all that, and select that option. For obviously I will be not using the default numbers. I will be changing it according to my stress strain curve. So IO can be set at the initial yield point. LS can be set at somewhere here where you have some nonlinear action, and CP can be set at this particular strain level where you, after which you have the collapse or this particular material. So I can give these numbers in compression and tension. Unlike concrete, now the compression and tension numbers will be same, because the concrete will steel will be modeled with same tensile and compression behavior in both directions actually. And obviously this is based on an assumption that rebars will not buckle. If we want to model the buckling also in our computer model, then we have to modify the stress strain curve in the compression side of the material stress strain curve. We will not take it up to the yield point, but we will assume that the bar will fail at the critical buckling load uh, in compression, but in tension we will use the full curve. But assuming that we will not have buckling in our bar, we can have the complete stress and strain behaviors in both tension and compression sides. We can just click OK after giving all the inputs and give this material some name. Let me call it as nonlinear steel. So now we have two materials which should be assigned to our concrete and steel fibers. They have their stress strain curves. So we are done with the first step. The second step is to actually define the cross sections of beams and columns. Let's say in this case we are only modeling columns as nonlinear. So I will going to be defining section properties and frame sections. I can add a new property, reinforced concrete rectangular cross section. And for the purpose of this demonstration, let's assume that this is my cross section and it has a material which is now nonlinear concrete, and I should provide the concrete reinforcement also. So I should actually provide the number of bars and their spacing in and clear cover and everything. So please check this form which allows you to provide the longitudinal number of bars and the confinement bars, which is the transverse reinforcement, their diameter in terms of numbers if you are using US designation. The materials for both longitudinal bar and confinement bars can be different also, but for our case let's assume that they are the same nonlinear steel which we have just defined. And this is the design option. That this won't affect our nonlinear analysis results, but you have to provide all the reinforcement for our cross section. Let's assume that we have this reinforcement, this cross section size, and let's say these are my all columns. So these are columns, let me call them columns. And obviously you have to provide the crack stiffness modifiers also, because we will be having the material fibers only at both ends, maybe equal to the 10% of the length on one side and 10% on the other side, but in between we will have an elastic column. And whenever you have an elastic component, you must provide the crack stiffness modifiers for that. But for inelastic components, there is no need to define these modifiers, because the inelastic action is explicitly modeled and there is no need to define these implicit factors. So I click OK, and this is my columns cross section, and I add a new beams cross section, for example. Sorry, add new property and rectangular, let's call them beams. And let's assume the same properties, nonlinear concrete. It is a beam now, and it is simply asking you to have a top and bottom reinforcement. But in this particular model we will be only modeling columns as nonlinear, so therefore it doesn't matter you provide the beam reinforcement or not. But if you also make or model beams as nonlinear and want to use an auto option in program, the program must know the reinforcement in your cross section. So for beams I can just click OK and click OK. So the second step is also done, which is the definition of cross sections. Now the third step is actually to draw the element first, and then the third step will be to actually assign them with the plastic hinges or fiber hinges, actually telling the program that these columns are nonlinear, and therefore the fibers should be included in their nonlinear model. So let me quickly draw the beams. Maybe this quick draw frame option, and in that let me first select the beams. So let me just okay, it also draw the columns also. So let me just undo it and again use the same quick draw option and select the cross section as beams, but this time I draw it like line by line. So I draw all the beams, right, like this, and then again I select the columns and draw all the columns like this, So now my two-dimensional frame is complete. Let me just quickly select the bottom nodes, 4 points, and then assign the fixed support condition at the base. So this is fixed support, all 6 degrees of freedom are restrained, and click OK. So actually the geometry is completed, but now we have to go to define and section properties, and in that we have to define this hinge properties. In this hinge property, I can click on add new property, and it is the default, it should be actually concrete type, default for concrete. And here I have to give a name of this particular hinge. So let me call it as material fibers, material fibers. And here is the hinge type. It can be a brittle hinge type, which is called force controlled, and a deformation control, which is a ductile hinge type. Actually, if you want to model nonlinearity with respect to the deformation measures, and provide the hinge properties in terms of deformation measures, then you can go for this ductile option. If you want a, you can say, to model inelastic action in terms of forces, for example, you want to capture a particular force limit state or force failure. In that case, you can go for the force control option. In our case, we will be using ductile or deformation controlled hinge, because fibers have the nonlinear stress strain materials, and in terms of stress strains we have the acceptance criteria. So we will be using this ductile option, and in that list these are all the inelastic hinges, type of hinges which are available in deformation controlled type. So we will be selecting this fiber PM2 M3 option, because this is used for the fiber modeling. And when I select that one, it asks me two things. First is whether the program should actually divide your cross section into fibers according to his own decision, or you want to define line by line each fiber, giving their properties like area of that fiber in a particular cross section, material of that fiber, and the location of that fiber. These things you want to give it to each fiber by manual entries, or the program can automatically divide based on his own decision. So I can quickly show you both options. If I go for user defined and click on define show fibers, it will open a new window for me in which I can add each fiber as a new entry or a row in it. For example, I can say this is fiber number 1, and it should be applied to my columns cross section, and then I have to provide the area, enter the area, then coordinate 3, which is the x coordinate. Let's say if it is located at the corner, I must manually calculate the distance from origin to the center of that fiber in x or 3 coordinate and 2 coordinate, and what is the material associated with that. So I have to select a material also, and this whole list I have to populate myself fiber by fiber. So let's say if I have 4 bars at one at each corner, and I divide it like 3 by 3 cut, so which means I will be having 9 concrete fibers plus 4 steel fibers, a total of 13 fibers for this cross section. So I have to enter 13 entries manually. The second option was that I just allow the program to divide my any cross section based on his own decision. So it will divide my cross section in a grid manner, and then it can also assign the corresponding material stress strain curves and assign the areas and location also. So since all the information is already available with the program, the cross section is already defined, the reinforcement is already given, it can do it for me automatically also. The second thing I have to provide here is that how much is the hinge length. If I click on relative length and give 0.1, which means that 10% of the total length should be actually given with model with the fibers or hinge, right? So if I go for this 0.1 and assign this hinge to both ends of my column, 10% at one length at one end and 10% at the other end will be my fiber length, and in between 80% of the column will be elastic frame element. If I want a particular value, I can uncheck this relative length and give some, let's say, 150 millimeters, because millimeters are my length units. So it will be 150 millimeters length of the hinge, right? So it is distributed plasticity. It You have to give a finite length of the hinge if you are using the fiber modeling approach. So let's just say for the simplicity that the 10% of the length of each column, which will be assigned with these fiber hinge, should be modeled with the hinge length, and other length, remaining length, should be elastic. So I click OK, and currently if I just click OK, this material fibers named hinge will be defined. Currently it is using the auto option, which means whatever section I will assign this hinge, program will divide it into material fibers based on his own decision. I do not have any control on the number of fibers and the materials of each fiber and the location of each fiber. Program will do it for me, and I can review it after assigning this hinge to a particular element. So after that, I will be just uh, clicking OK and then OK. So my fiber hinge is defined. This is one fiber hinge which is using the auto option, and its name is material fibers. I can click on show hinge results to show it some of its property, that what is the type of that hinge, what is the behavior, and whether it is a auto generated by the program or you have defined it. So the generated option is no, and it is not generated from any other hinge, so therefore it is not applicable. If I say show generated properties, there is no other hinge which is auto generated by the program. But if I click OK now, and now I am ready to assign this particular hinge to both ends of my columns. So I will be selecting let's say all 16 columns in my model. So you can see here that 16 frames are selected. I will be going to assign and then frame, and there is an option called hinges here. So I can assign that auto hinge which I just defined to both ends of my columns using this option. So I click on hinges, and here I have to select the hinge property, and then at what distance I want to assign that hinge along the length of that column. So there is an auto option by default available if you want to use ASCE 41 approach for the modeling the hinges. That is a different approach than fiber modeling. In that case, you will be using this auto option and click on add hinge. It will redirect you to the ASCE 41 tables and everything. But we will be using fiber hinges. So this material fibers is the hinge which I have just defined it, and here I have to tell the location of that hinge along the length of that column or whatever element I have selected here. So I say that okay, it should be assigned at a relative distance of 0, which means exactly starting from one end, and click on add hinge. It is added, and then I said relative distance of 1 and again click on add hinge. This means that I am telling the program that this hinge should be assigned at both ends. And while defining that hinge, we defined its length as 10% of the length of the element. So at both ends, 10% of the length will be assigned with fibers which have a concrete stress and strain nonlinear already assigned. So if you just look at the hierarchy, how we did, we first defined a nonlinear material. We use that nonlinear material in my defining my cross sections, and then those cross sections are used to define or draw the elements. And now in those elements I am selecting and assigning them the hinge. So the program will automatically develop or generate the hinges for these selected columns. So I click apply and click OK, and here you can see that this green symbol is showing that an auto generated hinge, which is a fiber hinge, is assigned at both ends of the each column which was selected. So here if I zoom in, you can see here that these are the material the name of the hinge which the program have actually uh, calculated or determined or generated is 59H2, and in bracket it is showing that what was the original hinge which is used to generate this additional hinges for each of these columns. So now if I go back and want to see again what are the additional hinges which program have auto generated based on my column cross sections and reinforcements and materials, I can go to define and section properties and hinge properties again, and this time you can see that all of the table is populated. The first hinge I defined and all the remaining are generated by the program. They will only be visible if you just click on this show generated properties here. So their generated option is by default yes, which means that they are generated by the program from this hinge which was the master hinge material fibers. Let's just select any general or random hinge. Let's say this one, and click on modify show property, right? And go on the modify show hinge property and click on define show fibers. You can see these are the two same options which we have defined while defining the first master hinge, and others are generated from that by the program automatically. I can click on define show fibers, and this will show me the completely populated the table for each of the fibers. If I click on a particular fiber on particular row, we can see that what is the area assigned to that fiber, what are their 2 and 3 coordinates, what is the nonlinear material associated with that. So you can see that this program have defined 8 steel fibers. Probably there were 8 steel bars in that, and then the remaining, out of those remaining 25 are the total number of fibers. 8 are actually for steel, and the remaining are for concrete. So it automatically defined the nonlinear concrete and steel based on the amount of reinforcement and the size of cross section and everything. So this column, whatever we have selected currently, you can see that in the view, is assigned uh, uh, with a with all the concrete and steel fibers automatically. If you want to modify any property from auto generated hinge, you can, I think, uh, convert it into user property. You can check that option when it is available, and that in that case the program will allow you to modify that hinge also. So you can check some of your hinges, auto generated hinges, and confirm that they are correct, and then that was the last step in the fiber modeling. Now you are ready to run a nonlinear analysis in which the columns will be behaving like a nonlinear columns modeled using fiber modeling approach. So quickly, the last step I can show you here, when you define a load case, now you can actually define a nonlinear static or nonlinear dynamic load case, because your model have some nonlinear components in it. So if I add a new load case, and now I can select it as static, and now I can go for nonlinear option, and other things will be similar, like we have to define a load pattern and we have to select that pattern and give a scale factor, and then there are some additional parameters for nonlinear analysis, like the load should be applied full, it should be force controlled or deformation controlled, and the results should be saved for each step of the analysis or the final state only, because nonlinear analysis is not just one step analysis. The load will be applied, if you make it nonlinear, it will be applied in a step by step manner, and you will be providing those number of steps into this last option, which is the maximum total steps, these ones, like let's say 200. So whatever load is in that particular pattern will be applied in 200 different steps, and with each step you can save the results by just clicking on multiple states and then selecting the numbers here, and then program will be able to tell you the damage of the structure as the loading is applied in a step by step manner. This is for static analysis, but if you want to go for nonlinear dynamic analysis, you can select time history, and again this can be nonlinear. Now you can select your time history acceleration pattern, which is the ground motion in this case, from here, whatever you have defined earlier, and then click OK. And once you, for example, click OK, you are now ready to run the actual nonlinear analysis. So let me just add just any random load pattern and click OK. So now this is your nonlinear static pattern which is ready to be run. And once you run this analysis, you can actually see with the deformed shape, you will actually be able to see the damage of your columns because they are nonlinear now. If any loading which is beyond their cracking or yielding or ultimate capacity, the program will be able to tell you after the analysis, and you can check the performance using different performance check options available in SAP. And then you can check whether the acceptance criteria of IO, LS and CP was met under a particular loading or not. So this was a quick demonstration about how we can use fiber modeling in SAP 2000.